The equation of the straight line L is that R is 1, 0, 2 plus T, 1 minus 1, 0. Find the position vector of the point P on L such that OP is perpendicular to L. Right. Well, the first thing we need to do is to kind of work out what the question is on now. So what have we got here? We've got a straight line that's given there by an equation. We've got an origin that's over there, and P is some point on that line. And according to this, you know, as T varies, P is in different positions, and we want the particular point where P is, where the line from the origin to P is a right angle. That's what we're interested in. There we go. So that means that the vector OP and the vector that is the direction vector of this line must be perpendicular. And two perpendicular vectors, how do you know they're perpendicular? Dot product is 0, because cos theta would be cos of 90 and cos of 90 is 0. So what we want is to find, we've got the direction vector of that line. That line is 1 minus 1, 0. That's its direction vector. We need some expression for the vector from the origin to P. Well, if P is on this line, then there must be some value of T. You know, as T varies, it gives us all the values of T. So OP, another way of writing that, is to say it is the vector 1 plus T minus T, 2. Can you see what we've done there? We've just taken that and put it all together to give us one vector. So, if it's perpendicular, then when we do the scalar product of 1 minus 1, 0 with 1 plus T minus T2, we must get a result of 0 because they're perpendicular. Actually, it's not that difficult, is it? Once we get to this point, this is quite soon going to give us a fairly simple linear equation. I don't need to write that last bit. We end up with 1 plus T equals 0, which just says that T equals a half. No, it doesn't. It equals minus a half, doesn't it? Is that right? 1 plus 2t equals 0, so t equals negative a half. The question didn't say find the value of t, though. It said find the position vector of p. So the position vector of p is 1 plus minus a half, minus minus a half, 2, which gives us a position vector of a half, 2. And that would be it. That's quite nice for 3 marks. This is quite a common trick though, isn't it? This idea of coming up with a general point on a line by merging your equation of your line together into one position vector. And it's quite a useful thing to remember how to do. A point Q is on L such that the length of OQ is 3 units. Find 2 possible position vectors of Q. Well, we're going to now, this is going to be slightly awkward, but we're now going to deal with this the same way. So we're now going to say that the position vector of Q is, what did we have before? 1 plus T minus T 2. And the question has said that is equal to 3. Q is equal to 3. Well, this is now just using our how we find the length of a vector, isn't it? The magnitude of a vector. It would be, well, we'll do it with the square root in there, and we'll get rid of it in a moment. The square root of 1 plus t squared plus minus t squared plus 2 squared is equal to 3. And we've ended up just with a little bit of algebra in here. I don't fancy that square root sign, so I'm going to change this. So we've got 9 over here by square root on both sides. We've got 1 plus t all squared. We've got t squared, and we've got 4. And we appear to be heading for a quadratic. What is that? Is that minus 4? That we end up with? I think so. Okay, which factorises as t, what would it be? Plus 2 and minus 1. So we get t equals minus 2 and t equals 1. The question said find 2 possible position vectors of q. So we now need to sub these values of t back in. So if t is minus 2, we've got 1, take away 2, minus minus 2, 2, and the other possible value is if t equals 1, we've got 2 minus 1, 2. There we go. And we can see that both of those, you'd get the same value, wouldn't you? You'd get 2 squared plus 2 squared plus 1 squared gives us 9, square root of which is 3. There we are. That's quite neat as well. Another 6 marks. And that's